Hi there, this is Richard Walker from Lucidate. In this and the next few videos, we will explore ensemble methods of machine learning. In this ensemble mini-series, we will look at an improvement to decision trees called random forests, as well as introduce some terms such as boosting and bagging. The concept of ensembles is straightforward. Combine the results of several different models to get a better overall result. To gain an intuition of how ensembles improve accuracy, consider the following situation. We have three machine learning algorithms, H1, H2 and H3. Each of them has a solid but unspectacular accuracy score. H1, an accuracy of 71%, H2 of 70% and H3 69%. Let's draw a Venn diagram depicting each model's performance on a sample dataset. We'll use the circles in the Venn diagram to show where each model makes an incorrect classification. H1 will get things wrong 29% of the time, that's shown in green. H2 gets predictions wrong a little more often, and this is shown in yellow. H3 will be incorrect most often, and it has the largest circle, coloured red, which represents an incorrect classification 31% of the time. If the classifiers work exactly as illustrated, then we can combine them to form a perfect classifier that will never get a single sample wrong. How can we do this? Well, we simply allow them to vote and take the majority prediction. There is no area on this chart where two or more classifiers get the prediction wrong. To observe this, take the purple point. If it's in this area, then all of the classifiers will predict the correct outcome. If the sample is in this region, then our most accurate classifier, H1, will incorrectly assign this sample. However, it will be outvoted by the two weaker classifiers that will get the prediction correct. No matter where the sample is, there will always be a correct aggregate prediction from this ensemble of voting classifiers. Now, clearly, the real world is not nearly so forgiving. We would be extremely fortunate to choose a bunch of classifiers where each one covers the blind spot of every other. Our perfect ensemble will only be possible if all of our classifiers are independent, making uncorrelated errors. In reality, there will always be an overlap in areas where two or more of our classifiers get things wrong. This is the situation shown on the screen, with intersections between the areas where two or more classifiers are incorrect. With models trained on the same dataset, it is all but inevitable that there will be significant overlap in misclassification. These are areas where there will be majority voting for the wrong outcome. This initial point would be correctly classified. While H2 gets it wrong, it will be outvoted by H1 and H3. But in this region, all three classifiers make the wrong prediction. We'll find many samples where none or only one classifier is incorrect, and here our voting scheme will work. But if we find ourselves in any of the intersections of incorrectness, such as here between H3 and H2, our voting ensemble will produce the wrong result. If we build a tree from the model accuracies, we can come up with a simplified kind of back of the envelope measure of accuracy of the ensemble. At our root node, we have H1 and a 71% chance of a correct prediction and a 29% chance of a misclassification. H2 has a 70% chance of being correct and a 30% chance of being wrong. If we sum up all the chains of probabilities and look at the outcomes, where we get at least two correct classifications at the leaf nodes in our tree, we come up with a figure of 78.4%. greater than any of the individual classifiers. So to benefit from this diversification, we need different classifiers. There are three ways we can achieve this. Firstly, use different models. That is to say, we can combine the results of different techniques or algorithms. H1 could be k-nearest neighbours, H2 could be a decision tree, and H3 a neural network. Secondly, we can choose a different set of model hyperparameters. For instance, we could train several neural networks with different numbers of layers and different numbers of neurons per layer. The URL on the screen is a link to a Lucidate video where we combine multiple different neural networks to achieve a much better ensemble performance than a single network on its own. And finally, we can use a different training dataset. In practice, we often use combinations of all three. Random forests are a great introduction to ensemble methods. Random forests use all of the diversification methods shown on your screen and typically offer very large accuracy improvements over single decision trees on which they are based. If you're unfamiliar with decision trees, then don't worry. Lucidate has an explainer video that describes how they're built, trained and used. The URL is on the screen and there is a link in the video description. Decision trees are easy to build and very easy to interpret, but they do have a tendency to overfit, meaning that they can perform well on the training data but aren't as good at generalizing when shown out of sample information. Random forests retain the simplicity of building and ease of use of decision trees, but are much better at generalizing and performing on data that they have not seen. Building a random forest follows a simple set of steps. I'm going to introduce the term bootstrap here and explain what this means in a couple of minutes. Stay tuned. 1. Create a bootstrapped dataset. 2. Randomly exclude some of the features in this bootstrap dataset and build a bespoke decision tree from this smaller sample. 3. Use sample data excluded from our bootstrap step to determine the accuracy of this tree. Now we're going to talk about this third step in the next video and focus on the first two steps here. So, what do we mean by bootstrapping in this context? It simply means creating a new training data set from our existing data. The way we do it is take random samples from our training data with replacement. That means that we allow duplicates in our bootstrapped dataset. Furthermore, we keep the amount of data the same. That is to say, if our original data has 20,000 records, then our bootstrap data will also have 20,000 rows. So, as well as having duplicate rows, our bootstrap training data will have records missing that were in our original data. Bootstrapping and aggregating the data with replacement is referred to as bagging. So here's a simple example of bagging. If our test dataset consists of just these 20 records, then we'll take samples from this dataset with replacement to build a new dataset of exactly 20 records. This will result in duplicates, as you can see here, as well as some of the original data being left out. The next thing we do is build a decision tree from this bagged data, but with an additional element of randomness. Instead of using the full dataset when we split at each node, we randomly exclude columns from our bootstrap data. This results in a reduced feature set. We then search for the optimal split from this smaller dataset, and we repeat this process of randomly discarding columns for each split in our tree. Again, if you're unfamiliar with splits, Gini impurity, and how to build a decision tree, then Lucidate has an explainer video on the topic. Please see the link in the description. So this will result in a diverse set of trees, all trained on their own bespoke dataset. We then get these diverse set of trees to vote. The human analogy here is the wisdom of the crowd. If you poll thousands and thousands of people and aggregate their answers, you nearly always get a better answer than if you query a single expert. A typical random forest will grow thousands or tens of thousands of trees, and despite their simplicity, they're one of the most powerful machine learning techniques available today. The power of random forests is that it creates an uncorrelated set of decision trees. It achieves this by using a different set of data for each tree and a different feature set for each split of each tree. This is brought about by bagging and feature selection. We can see here dramatically improved performance across all of our metrics for a random forest over a single decision tree. Random forests are used extensively in financial markets for fraud detection and loan approval, as well as in healthcare for disease prediction. In the next video, we will look at some further benefits of the random forest approach. This includes dealing with missing data, identifying feature importance, and reducing overfitting.